Okay, so plotting absolute value functions, and we're looking two-dimensional, and for each of the following functions, sketch the graph and state the range. We're going to analyze this as part of the sketching. So the first one there, because you can see we've got two examples, that we have the absolute value of x minus 3, then we add 1 on. So we've basically got, for this one here, we need to look at the domain x is greater than or equal to 3. So if we have that, we'll have in the absolute value part of it, we'll have, if you think about that, if we have 3, we'll have 0 in there. If we have anything above 3, we'll have a positive value inside the absolute value symbol. So that's one of the situations. We also need to look at the complement of that when x is less than 3. If we consider that first one, when x is greater than or equal to 3, f of x will be greater than or equal to 1. When x is less than 3, so in this part here, we'll have a negative, but when you take the absolute value of a negative, you get a positive, and then if we add 1, it won't go any lower than 1, so it'll also have its values at least 1. Now, as x gets greater in the positive direction, f of x will keep getting greater, and as x gets lower and lower below 3, f of x will keep getting higher as well. So you'll have an interesting sort of shape. Just taking a slightly simpler version of that, if we have just, forget about the plus 1 bit on the end, if we have just x minus 3, we get the red line there. So it's a straight line, and with an y-intercept of negative 3. Look what happens when we take the absolute value of that. Okay, so we've got anything that goes below the x-axis gets reflected, so it actually gets reflected about the x-axis. So it never dips down due to the absolute value nature. Then if we put a plus 1 on the end, that's moved that first graph up. That would be the same as the graph of x minus 2. And the second one, so it's moved that one up as well too. Did you see that? So it's there, add 1, it's moved up 1. See? Alright, one last time. Okay, well, I lied more than one time. So hopefully you can see that there. So it revolves around the point 3, 1. Looking at the next one, negative of x minus 3 absolute value plus 1. So we've got negative in front of the absolute value there. So let's have a look then at those same situations when x is greater than or equal to 3. Inside the absolute value there, we'll always have a positive, and then a positive times, we'll take the absolute value of a positive, and then we get a negative plus value plus 1. So if we've got x less than 3, we'll have a negative inside there, and if you have a minus b, and if a is a negative, you can say that it's, or negative a plus b, well, it might make it a little bit easier to see. That's the same as b minus a, and so we could say it's 3 minus x. Okay, so it swaps the order around when we've got a negative inside the brackets there, and we've got negative 3 plus x plus 1, or that equals x minus 2. So it behaves like x minus 2 when x is less than 3, whereas this one here behaves like that, which is the same as negative x plus 4, or you could say it's 4 minus x if you prefer. So it behaves like 4 minus x or negative x plus 4. So it's going down once you got at least 3 on the x-axis, and then if it's less than 3, it's got a positive gradient with negative 2 as its intercept. Notice how it rotates around that point 3, 1, okay, like the other graph did there. So it behaves a bit like two functions separated by the point 3, 1, two linear functions. Notice the characteristic V shape of the absolute value of a linear function. These are often called just absolute value functions, in fact. So what about if we've got other sorts of functions? We've got an absolute value of what essentially looks like a quadratic, and then we've got an exponential there. What goes on? Well, if we have a look at the graphs, just to speed things up a bit, we can see the following here. For the first one, if we've just got basically what we should be familiar with a quadratic like that, if we basically find the absolute value, then enter that in, y equals the absolute value of x squared, take 4. Hopefully you can see what goes on. So we've got the bits that have the f of x or the y value in the negatives are reflected back up to the positive. So it behaves like the original function for all values such that f of x is positive or y is positive, but once it's negative they're reflected up. So those negative values are reflected in the x-axis. Same thing will go with the other function. The other function being 2 to the power x minus 1. So you can see the green line there, 2 to the power x minus 1, and then the absolute value of 2 to the power x minus 1, and again all the values where y is negative are reflected due to the absolute value nature of it, and we get the curve in black there. So the idea is to look at the domain and range for which the y values are negative in the original function and they get reflected. So values for the domain that create a negative y value, those bits are reflected above the x-axis. So we just saw examples of y equals the absolute value of f of x. We also need to get familiar with y equals f of absolute value x. So when we're subbing in absolute values of x, what happens? And here's two examples here. So we have a different sort of quadratic. Let's see what happens there. Here we see the original quadratic in green, and then if we look at f of absolute value x, we have a reflection occurring there. Now it's different to last time. This time the reflection occurs in the y-axis. So we can look at why that is. This phenomenon happens when we go below x equals 0, we go into the negatives, it turns the x back into positive, and so as we go further and further in the negative x direction, so if I can just get my little pen up, if it'll behave itself, and so yep, so as we go this way, the curve will behave as if it's like positive, so they are negative x values, but the corresponding y values will be the same y values as per the ones of the positive value of that. So yeah, you can see why that's reflected in the y-axis. So when we have the f of absolute value x, it's reflected in the y-axis. So the last example was 2 to the absolute value x. So we know the shape of 2 to the x, but what about 2 to the absolute value of x? So there's 2 to the x and there's 2 to the absolute value. And again, once we get into negative values for x, so we've got, let me get the correct tool happening here, should be a pen, there we go. Once we get to negative values of x, which means there, and heading that away, it starts to take on the y values as if it were positive. Alright, and that's of course, it basically is negative inside there, but the effect due to the absolute value is positive. So if we have 2 to the 1, we've got 2 for the y value, and if we've got 2 to the negative 1, alright, and so when x is negative 1, we take the absolute value of that, and that'll still come out as 2 to the 1, and it'll give a y value of 2. And Same with squared, same with cubed, same with all real numbers. So if we have f of, let me just get that to work. So if we have f of the absolute value of x, it's reflected in the y-axis. That's when x gets below 0. Whereas if we have y equals absolute value of f of x, any negative y values are reflected back up via the x-axis into the positive y.